Hello class, this is the video about section 5.2, right triangle trigonometry. So remember that a triangle in which one angle is a right angle is called a right triangle, and that the side opposite the angle is the hypotenuse. Also, we're going to need the Pythagorean Theorem, which states that if A, B, and C represent the side lengths of a right triangle, and C is the length of the hypotenuse, then A squared plus B squared is equal to C squared. So you'll see in this first example the type of problem that we use this theorem in. So let's say that you're given a right triangle and the hypotenuse has a length of 5 inches and one side has a length of 2 inches. Then we can find the length of the other side as follows. By the Pythagorean theorem, x squared plus 2 squared equals 5 squared. So this is a quadratic equation we can solve using the square root method. Let's simplify a little bit first. So x squared plus 4 equals 25. And now we can subtract 4 from both sides. X squared equals 21. So when we solve this, we take the square root of both sides. So x should be plus and minus the square root of 21, but because we're talking about the length of a side of a triangle, we should reject the negative answer. So what we can say is that x is equal to the square root of 21. Okay, so we'll be using this theorem extensively in the sequel. One more definition. If theta is an angle between 0 and pi over 2, it's called an acute angle. Okay, so number 2 is really a group activity. I'm afraid I might not be able to do this, but I can show you what it is if you want to try it at home. You'll just need a ruler and you'll have to do it by yourself. So the idea is that we're going to draw a big right triangle, and the side lengths are, say, A, B, and C. I just label them however I want. And then inside of this right triangle, I'm going to draw a smaller right triangle sharing the same acute angle. So for example, it still has this angle in it. So maybe the smaller triangle is this one here, right? So I can label the pink sides A prime, B prime, and C prime. So these are similar triangles, they just share an angle. And then what you can do if you want at home, try to draw the big on a piece of paper, measure out all the lengths, A, B, C, A prime, B prime, and C prime with a ruler. Try not to round at all. And then fill in the table using your calculator to convert fractions to decimals. So whatever the length of A over the length of B is, and then you'll find the length A prime over B prime, and so on. Okay, so if you want to do this, go ahead and then compare the two columns of the table and see what kind of patterns you can find. So if you did do the activity, the thing that's cool about it is that because everybody will have their own triangle, I don't know what numbers you're going to get for your answer, but I do know that these two should be at least almost the same. There's measurement error, rounding error, human error. They might come out to be not exactly the same, but similar. But all of these ratios, so A over C to A prime over C prime, will be the same, and so on. So each of these similar triangles will have the same ratio. So although the side lengths are different, their quotient, when you divide them and turn it into a ratio, is the same. So what this tells us is that this ratio is a function of the angle only, not of the triangle. It does not matter whatever the length of the sides of the triangle are. If I divide the length of any two sides, then I get the same number. So what this means is that, as stated in definition 4, by looking at all ratios of side lengths, we are able to define the 6 trigonometric functions. So it's important to note that these must be relative to the triangle under consideration. So everything in my table is relative to this triangle. So theta is the acute angle. And then this side is what I call B, which is the side that's opposite of theta. And then A is the side that's adjacent to theta. Okay, and then C is the hypotenuse. If you will have drawn a different triangle, so say you put theta in here, then this side, which is opposite of theta, would be B, and this side, which is adjacent to theta, would be A. C is still the hypotenuse, though. Hopefully that helps you understand. Okay, and then we have this little cute shortcut thing, which is SOHCAHTOA. This helps you remember the names of each of the ratios, because as you can see, the sine of theta, which is abbreviated sin of theta, has the value B over C. So that's what this is saying. This is saying that the sine of theta is equal to the opposite O over the hypotenuse H. So that's what the OH is in this SOH. So sine of any angle is the opposite side over the hypotenuse side. Okay. The C part is that the cosine is the adjacent side over the hypotenuse. And lastly, the T is that the tangent of theta is the opposite over the adjacent. So these are functions, but these are also just the names of the ratios. So that's how you can remember them. It's by SOHCAHTOA. You'll see that there's 3 ratios from SOHCAHTOA, and then there's 3 more ratios in the table. So we talked about sine, cosine, and tangent. We also have the cosecant, secant, and cotangent. So the cosecant is equal to the hypotenuse over the opposite. The secant is equal to the hypotenuse over the adjacent, and the cotangent is equal to the adjacent over the opposite. So all of the values are given in this table here. Okay. For me, the easiest way to remember the other ones, if I don't have SOHCAHTOA, is that cosecant is 1 over sine. We'll talk about these identities more later. Secant is 1 over cosine, and then cotangent is 1 over tangent. So I really only just remember the 3, and then from there I'm able to get the other ones. Okay, so let's see a concrete example of how this all works. In problem 3, we're given that the sine of an angle alpha is equal to root 2 over 2, and we want to find the remaining 5 trigonometric functions of the acute angle alpha. So the way that you have to understand this problem is that we have a triangle and we have an acute angle, so not the right angle, but either angle. We can say choose this one, it doesn't matter. And we're given that the sine of alpha is equal to root 2 over 2. And we remember that sine is equal to the opposite over the hypotenuse. That means that root 2 is the opposite, and 2 is the hypotenuse. So I can find the adjacent side, which I need, as in problem number 1, by using the Pythagorean theorem. So I know that root 2 squared plus x squared is equal to 2 squared by the Pythagorean theorem. I can simplify this and then use the square root method to solve for x. So I have 2 plus x squared equals 4. Subtracting 2 from both sides gives me x squared equals 2, which means x equals root 2. Again, I reject the negative because we're only talking about side lengths. Okay, so x is equal to the square root of 2 by the Pythagorean theorem. And now I can use the table above to get all of the other trig functions. So SOHCAHTOA will let me get them. And then remembering that because sine and cosecant are reciprocals, I know that the cosecant will be 1 over the sine. So whatever I got for the sine, it's the opposite for the cosecant. Okay, so 2 over root 2 is fine with me. Some of you will want to multiply by root 2 over root 2, and then you can say it's 2 root 2 over 2 or root 2. So I don't mind if you want to keep it like this or keep it like this. That's just two different ways to write the same answer. Okay, so then similarly we can find everything else. So the cosine is equal to the adjacent side over the hypotenuse, and that means that the secant is the reciprocal of cosine. So the secant is there. And lastly, the tangent. Tangent is equal to opposite over adjacent. So I would probably go so far as to simplify that to equal 1. And then I know that the cotangent is the reciprocal of tangent. 1 over 1 equals to 1. So this is how you can solve these problems using a right triangle.